Welcome everyone to Scientists to Go. My name is Zoe. I'm an educator here at Gulf of Maine Research Institute. And today I am super excited for you all to be joining. This is our last Scientists to Go of the year. So thank you all for your support all year. Um, Scientists to Go is a program that we offer here at GMRI for students in classrooms to connect with researchers in the field and hear about what sort of experiences got them to where they are today. If you are an adult joining this meeting without students, that's completely welcome, but just here's a reminder to leave the discussion space open to voices and questions from our students that are on the call. Today, we are joined by Dr. Alix Contosta, who is joining us from the University of New Hampshire, where she studies how winters and spring phenology are changing. And this Scientist to Go is also special because it's part of the Globe Phenology, Spring Phenology campaign. Globe is a NASA-sponsored program that brings students together with teachers and scientists and citizens worldwide to promote science and learn about the environment. And GMRI is an organization that's partnered on this project. So you can learn more about Globe and how to participate by going to their website, which I will post in the chat, along with a couple other links. But for now, I'll just turn it over to Dr. Contosta.
Okay, good morning. Thank you for the introduction. So, my name is Alix Contosta. My official title is I'm a research associate professor. I work at the University of New Hampshire in two departments. I'm in the Earth Systems Research Center and I'm in the Department of Natural Resources and the Environment. And I do a lot of work talking about changing winters and changing seasonality to all kinds of audiences, including students like you. So I'm happy to be here today. Um, so my research tries to understand how changing winters and changes in the timing of seasons affect ecosystems and people. And I really like this picture because it says a lot. This is from a local recreation area near where I live and near the University of New Hampshire, where lots of people like to go sledding in the winter. And we've had a lot of winters where sledding looks like this in the past few years, where we have really patchy snow. It's sort of icy. The soil is exposed. This is not very fun for sledding, and it's also can be quite disruptive to natural ecosystems because the soil isn't protected from air temperatures that can get quite cold. We can see a lot of changes in the water cycle when we see precipitation falling as rain instead of snow or turning to ice when it gets cold. We can see lots of impacts on roads and infrastructure. So, a lot of my research is trying to understand how winters are changing and what the impacts are for natural systems and also for people that rely on ecosystems. And I got into this work. I didn't set out to do this. I didn't know that this is what I wanted to do when I grew up. I got into this work partly because I fell in love with winter when I moved to New England. So I didn't grow up in Maine. I did not grow up in New Hampshire. I actually grew up in Philadelphia, which is further south than we are now. And in Philadelphia, winters are a lot more mild. We had snow when I was a kid, but nothing like what we get up here. And I also grew up in a city, and so it would snow a little bit, and then the temperatures would get warm and the snow would get dirty. And I had no idea that winter could be fun. I didn't know that the snow could be a playground. And it wasn't until I moved to New England in the early 2000s that I had that experience of going out into the woods on snowshoes or just walking. I learned how to ski. And this is a picture of me in Grafton, Vermont, almost 20 years ago, trying to learn how to skate ski. And when you try to learn a new sport when you're an adult, it can be fun and challenging. And I fell down a lot. But I really fell in love with winter as this time to be outside and play in a way that I had not experienced when I was a kid. So that's part of why I got interested in studying winters. Um, or I got interested in winters, but I got interested in studying winters when I was in graduate school. So I did a lot of the research for my training, my scientific training down in Massachusetts at the Harvard Forest. And one of the key things that I studied as part of my research was what happens in soil underneath the snowpack. So there had been this belief in ecology for decades that in the winter, everything goes to sleep, that the temperatures are cold, that leaves fall off the trees, that even trees that have needles, like pine trees, like hemlock trees, aren't really doing a whole lot, that the system is dormant because it's so cold. But it turns out that in the soil, that's not true, right? The snow provides this really nice insulating blanket on top of the ground, and it keeps the ground from freezing, keeps temperatures above freezing, and all the life that's in the soil, the microorganisms like bacteria and fungi, insects that live in the soil, roots, can all be active during the winter. But we don't know a whole lot about what they're doing during the winter underneath the snowpack. And so, one of the things that I set out to study was what happens in soil beneath the snowpack. And here's just a picture of me. I'm in the front, and that's one of my student helpers in the back. We're coming out of the field. I'm dragging a sled that's loaded up with coolers that contain soil cores that we had taken. We had to dig through the snow to take soil cores from beneath the snowpack, to bring them back to the lab to do all kinds of analyses. And it's possible to take these soil cores from beneath the snowpack because the soil isn't frozen, right? Because the snow provides this nice insulating layer. And so I fell in love with winter when I moved to New England. As a playground, but I also got really interested in studying winter and especially what happens in soils beneath snowpacks as part of my training. As part of my training, as I worked on getting my PhD and becoming a trained scientist. And here's just a picture that I really like that sort of shows what life underground looks like across the seasons. This is from a paper that one of our graduate students at the University of New Hampshire published last year. And his research was really focused on arthropods, so insects and spiders. But this would be true for also microorganisms like bacteria and fungi. In the winter, everything above ground, looks really bare. The trees don't have their leaves on them. But then you have this thick snowpack that provides a lot of insulation. It's like a blanket. And beneath that, you have a lot of life, right? You have all kinds of organisms that are moving around. They're decomposing leaves. They're decomposing some of the organic material in the soil. They're recycling nutrients. They're breathing. You have water moving through this system. And so this is just a phenomenon that I find really fascinating, that it can be cold above where the trees live and where we walk around. You have this insulating layer of soil, of snow, and then you have soil that's alive below. It's something that's fascinated me for decades and something that I continue to study to this day. And it's really important to do this because our winters are changing. And so when I first moved to New England in the early 2000s, we still had a lot of cold, snowy winters, and that's not always true now. So here's a graph. This is from Climate Central, which is a really great website that provides all kinds of information about how our climate is changing. And this is showing how much warming has happened within each season, winter, spring, summer, and fall, since 1970. And you can go online to Climate Central and you can find graphs like this for cities all over the United States. I chose Portland, Maine because I think a lot of you are from Maine, but you could do this for other places. And if you look at this graph, you see we've got our four seasons, winter, spring, summer, and fall. And we see how much warming on average has happened within each of these seasons since 1970. And winter jumps out as the season that has experienced the most warming of all of them, right? We've seen a lot more warming in winter than we have in any other season. And so winters are really important. A lot of things happen in winter, especially beneath the snowpack in the soil, and yet our winters are changing. And also, something that's interesting is that winter warming is happening most places in the United States, but it's happening faster in New England, where we are here, than most other areas of the US. You also see similar levels of warming here in the upper Midwest. But lots of warming happening in Maine, in New Hampshire, in Vermont, and Massachusetts, right? So winters are warming faster than any other season. And that winter warming is happening faster in New England than most other places in the contiguous lower 48 states of the United States. And so studying how winters are changing and what that means for our ecosystems in New England is really important because we're seeing rapid changes and we're seeing them happen here. Okay. And one reason for the rapid warming is warming that's happening in the water that lives off of the coast of New England. So the Gulf of Maine is also warming very rapidly. This figure is showing an extreme warming event that happened in the Gulf of Maine in August of 2018. But the warming is happening not just in summer, but also in winter. And so we have this water body right off of our coast that is warming very fast. And what happens in the ocean isn't staying in the ocean. A lot of that warming in the ocean influences the conditions that we experience on land. And so we have these really rapidly warming winters in New England, and some of that is driven by warming that happens right off of our coasts. Okay, so changing winters can manifest in a lot of different ways. We can have less snow and more rain, so more midwinter rain events. So precipitation falls in liquid form instead of as snow. And if you love snow, that can be very sad. There's also many fewer days with snow cover, snow on the ground. This picture that I'm showing is of this sort of sensor tower at one of our sites close to the University of New Hampshire. And this picture is taken in the middle of February when you would expect to see lots of snow on the ground, but instead we see lots of bare patches, right? So we have less snowfall, fewer days of snow cover. We see earlier spring melt, right? So this is the river that flows close to my house, the Lamprey River. And again, this is, showing that spring breakup is happening earlier, that the ice is leaving the river much sooner. And we can also have a lot more extreme events. So, changing winters and overall warming doesn't mean that winter is never cold. We can also have really extreme cold snaps where it gets very, very cold for a few days and then it gets very, very warm. We can have this sort of whiplash between warm and cold conditions. So changing winters can include all of these different aspects. And this really matters. So changing winters, again, can include loss of cold temperatures, loss of snow, and this can affect our ecosystems and also the way that we live our lives. And so this is just an infographic that shows some of the impacts of changing winters in New England. And so on top here, I'm showing that there can be impacts to outdoor recreation. So fewer opportunities to get out there and ski, snowshoe, play pond hockey. And that, really also can affect the economies of our communities, places that rely on winter tourism to generate jobs. There can be impacts on water quality and flooding. So all these winter rain events that happen instead of snow can cause flooding. You can have earlier ice out dates for lakes. So there could be impacts on lake ecology because of that. There could be impacts on public health. So a lot of insects that we don't want, things like ticks and mosquitoes, they do well in warmer winter conditions. Wildlife can also experience impacts. You can imagine I've got this white snowshoe hare right here. This snowshoe hare turns white in the winter so it can camouflage against the snow. It turns brown in the growing season to take advantage of non-snow conditions. But you can have these white snowshoe hares against the brown background because the snow hasn't fallen, and that really can make them vulnerable. Lots of other animals rely on snow for habitat, and may also find it difficult to navigate through snowpacks that are more shallow or more icy. And then changing winters can also affect forest health. So, again, like public health for humans, there are insects that can affect trees, and they do well with warm winter conditions. And so, the warmer it is, the more we can have insects that damage forest health. And it can be very hard. Some places, a lot of winter logging happens to be able to access sites to cut trees to support the wood products industry. And it's hard to access those sites if you have conditions that are too warm because the access roads get really soggy and loggers don't want to go out there because they can cause a lot of impacts to soils and streams. And so lots of impacts of changing winters that can touch many different parts of our ecosystems and also of our human communities. Okay, but I also want to talk a little bit about spring. And so it's important to remember that winters are changing faster than any other season. But temperatures are increasing in other seasons, not just winter. And so this is the same graph I showed you before, where we're looking at how much warming has happened across our four seasons in Portland, Maine. And winter has seen the most warming, but you're seeing warming happening in spring and summer and fall. And so, spring is also getting warmer, and that has some implications for our ecosystems. Really, one thing to keep in mind is that it's not just that temperatures are getting warmer, it's that the timing of our seasons are changing, right? So we see warming happening in winter, we see warming happening in spring, but also when winter ends and when spring begins is something else that is shifting as our climate changes. And I want to show you an example of what this looks like that I think is pretty compelling. This is data collected at the Hubbard Brook Ecosystem Study. So Hubbard Brook is located right here where this red star is, right in the middle of the White Mountains of New Hampshire. And scientists have been collecting data there for over 50 years. And this really demonstrates the power of long-term data collection on the ground and how that can help us understand how our systems change over time. And what the graph is showing is time, right? We have 1955 through 2010 on our x-axis. And then what this is showing on the vertical axis is the day of year that the snowpack disappeared. When did the snow finally melt out at this site? And at the start of the record in 1955, the snowpack disappeared around April 22nd. And at the end of the record, it disappears around April 7th. And there's a lot of variability from year to year. And you know, that makes sense. You know that some winters are cold, some are warm. But the overall trend, right, if we draw a line through all of these points, the overall trend is towards earlier snowpack. And so over this 55-year period, the snowpack has been disappearing about 15 days or 2 weeks earlier. Right. So winters are getting warmer and they're also ending earlier. The timing of this season is changing. And the way that we measure snowpack disappearance, so snow depth and snow disappearance, is pretty simple, right? This is something that you can do yourself. You go out to the same location and you stick a ruler in the snowpack and you measure how deep it is, right? This is not a high technology kind of measurement, but if you do it again and again, day after day, year after year, you can start to build up a record of of what the snowpack looks like and how it changes over time, right? So This is what scientists have been doing at Hubbard Brook for the past 55 years. And the day that the snow disappears is when you see that, there is nowhere really to put your ruler into the snowpack, right? That's where snow depth equals zero. Okay, so winter is ending earlier. Spring is also starting earlier. So this graph is the same exact setup. We're still at Hubbard Brook in the White Mountains of New Hampshire, but instead we're looking at the day of year that the forest is greening up. I saw in the chat as people were arriving and responding to questions about the signs of spring, things like the snow is gone. Yes, right? That's what this previous graph showed. The snow is gone. But people were also putting in notes like, I see a lot of green, I see a lot of leaves, right? That is a sign that spring is starting. And so this figure is showing the same period of time from 1955 to 2010, but instead of showing the day when the last snowpack happened, when the snow disappeared, it's showing when the forest canopy, when all the leaves were in the trees of the forest canopy. And so that has also been changing over time. So at the beginning of this record in 1955, the forest canopy was greening up and closing on May 28th. And at the end of this record, it was greening up and closing on May 21st. And so that's an overall increase of 7 days if you put a line through this trend. Again, accounting for variation from year to year. And the way that you measure green up, again, is pretty simple, right? Scientists at this site go out. There are trees that they observe, same trees they've been looking at day after day, year after year for decades, and look for visual cues that green up is happening. So this is just a twig from a tree, and you can see, I think this is a beech tree. These would be the buds that have burst and the leaves that are starting to emerge, right? So you can go out and look for visual cues, which the globe phenology program is oriented towards, like, are the buds swelling? Have the buds burst? Are the leaves coming out? Do they look like they're fully grown? Right. Once these leaves are fully grown, then you can say, okay, green up has happened. So winter is ending earlier, spring is starting earlier, but the part that I'm super interested in is how these two things are not happening at the same rate. So if we put this whole thing together, right, we're still at Hubbard Brook, we're looking at change over time. So we're 1955 to 2010, and we're looking at the day of year that the snowpack disappears and comparing it to the day of year that the forest canopy has greened up and closed. And so we can look at this period or this window between snowpack and green up and how that's changed over time. So at the start of this record, there's about 40 days between when the snowpack finally disappears and when the forest canopy greens up. And at the end of this record, we've seen an increase in that period of 8 days. Right now, it's 48 days between when the snowpack finally disappears and when the forest canopy greens up. Because the snowpack is disappearing faster, winter is ending at an earlier pace than spring is beginning. And again, just remembering that the snowpack disappears when you stick that ruler in the snow, the number is zero. And you can use these really simple visual cues of what plants are doing in the spring to establish when green up happens. Okay, I'm almost finished because I know almost out of time. Um, so one thing that, I'm curious about is how this longer vernal window period, this period between snow melt and forest canopy green up, affects soil moisture during the following growing season. Because when you have this period between when the snow melts and when the forest canopy greens up, you have a lot of light, right? Here's just a picture of a forest where snow melt has already happened, but green up hasn't happened yet. And you can see all the light that's coming in. And there's a lot of potential for evaporation to happen, right? For things to get dried out during this period, which can affect how much moisture is in the soil for plants. just, to keep in mind that soil moisture affects the amount of water available for plants to use. And you can imagine a gradient of really wet conditions that are saturated. There's too much water in the soil, right? Here's a whole bunch of soil particles, and there's water in the spaces between these particles, and it's too wet here. Plants can't use all this water. That's one end of the extreme. And the other end is where it's too dry, right? There's very little water in the soil, except for tiny little films around soil particles that are so tightly held that plants can't access them, right? So there could be too much or too little. And the idea here is that if you have this longer period, this longer vernal window between when the snowpack melts and when the forest canopy greens up, you can end up with drier conditions. And we can measure soil moisture using a sensor placed in the soil. And so these are just two sensors that we're installing in soil in the surface and deeper down. This is actually at a site right behind Old Town High School in Old Town, Maine. And the sensor itself looks kind of like this. It's got these prongs on it, and you can measure soil moisture this way. And so this is something that my team and I have been trying to understand for about the past 10 years. And I have one figure to show you, and then I'll wrap up of what this is looking like. And this is data that we haven't published yet. We're working on a paper right now to try to understand this. But we're looking at how long the vernal window is, how many days are in this vernal window. Remember, this is how many days between snow disappearance to green up in the spring. And how does that compare to soil moisture? How much water is in the soil? We're measuring that with these sensors. What does that look like during the growing season in May, in June, in July, in August? And these are colors from just different sites. We've been doing this work, but the overall pattern is that if you have this long vernal window, it's 50 to 75 days, you see that moisture is lower during the following growing season. And you have this short vernal window, this short period between snow disappearance and green up, you have more moisture, right? More water that's available in the soil. So really trying to understand how these changes in our winters and our springs affect our ecosystems. Just in this case, using the example of how much moisture is available for plants to grow during the following growing season. So just to conclude, I have spent a lot of time in my career understanding how winter is changing. It's becoming warmer and shorter. Spring is also starting earlier, but this is not happening at the same pace. And this longer vernal window can reduce growing season soil moisture, which can affect plant growth. And these are all, lessons that I've learned from the past couple of decades of doing this work that has been inspired by, me falling in love with winter as a place to, or as a time to play outside, but also being really curious about what happens in the ground beneath the snowpack and how that's changing as our climate changes. So just thank you so much. And I think we're going to spend the rest of the time doing question and answer.
Thank you so much. That was really fascinating. I'm sure there will be a lot of questions coming in soon. If anyone has questions for Dr. Contosta, please throw them into the chat and I'll read them out to her. In the meantime, I want to point out that we have seven, maybe more, skate skiers in the chat right now. So they're very excited to hear about that, including a regional champion who's in sixth grade. So they're
Oh,
definitely watching
excellent.
it.
Do you want
Um,
me to stop sharing my screen?
sure, yeah, that'd be great.
Okay.
Um, but yeah, so while folks are thinking of questions, again, please put those into the chat. I have a couple questions for you. One of them is, what is something that you find really exciting about your field right now?
Um, well, this place that we live in is, I think I tried to explain this. Like, this is where some of the um, biggest impacts of warming temperatures are. This is where warming temperatures are happening in New England. And in the winter, this is where we see it the most. And so it's sort of a really important place and time to be doing this work. And so I find that exciting, like being sort of on the front lines of understanding how our climate is changing and what that means for for our ecosystems. It feels like a very uh, clear and present topic to investigate.
Yeah. Yeah,
So
we
I
talk
feel like that's pretty exciting.
yeah, we talk a lot here at Gulf of Maine Research Institute about how the Gulf of Maine is warming a lot faster than most bodies of water in the world and how that makes it a really good place to start doing this type of research. So we can kind of predict what will happen in other places. And it's cool that that kind of expands inland too. It's the whole region. Um, okay, we have one question that is asking, is it okay to equate the vernal window with mud season? Would
That's
you?
a great question. And I'm very happy to see Ed Lindsay here. He's a teacher that my colleagues and I have been working with for, I think, 6 or 7 years now in Old Town. Yes and no. So the mud season is, someone else, earlier in the chat was talking about our fifth season, the mud season, in addition to winter, spring, summer, and fall. The mud season happens during the vernal window, but it doesn't mean that conditions are always muddy during that period between snow melt to green up. So mud season happens often following snow melt when conditions can be really wet, partly because of the snow melt, and the trees haven't greened up yet. And what I didn't talk about, but is I think good to keep in mind, is that when the leaves come out on trees, photosynthesis happens, right? It starts to happen, and photosynthesis uses water, right? Like one of the key ingredients for plants to make their own food is water, and they get that water from the soil, right? So you have trees that are starting to photosynthesize, and they're removing water from the soil, and it leaves the leaves as water vapor. And so mud season, one of the reasons why it happens is that you have a lot of water in the system, and it is not escaping through plants, right? So it can be quite wet and muddy, but that doesn't always happen every spring, right? You don't always see mud season occurring because there are lots of conditions that can make mud season really good or bad. And so it can vary quite a lot from year to year. So the timing of mud season happens in the vernal window, but it's not exactly the same thing. There are other questions. I could go on and on about the mud season thing, but I'll maybe answer some other questions.
Um, okay, so another question is where and what do you hope to be doing in 5 or 10 years from now?
Okay, that's a great question also. I don't know that my actual job will be that different. So I'm a professor at UNH, and I really love my job because I get to teach, and I also get to train and mentor students to, become scientists, and I get to go out in the field and make a lot of measurements. I do plan to continue a lot of this work trying to understand changes in the winter and the spring and what the impacts are on growing season ecosystem processes. But um, I a lot of the work that I've done on this in the past has focused more on plants and uh, and I'm focusing now more on water. So really thinking about the implications for water resources and water cycling is where my research seems to be going with a lot of these questions.
Um, okay, a few more questions have come in, so let me scroll
Mhm.
back up.
Yeah.
Um, have you seen any changes with your job given new technologies like AI or other technologies that have come out recently?
Yes. Um, and some of them have been positive and some of them not so much. And so I do a lot of work with data. We have a lot of sensors that are installed in many different sites throughout New England that are measuring soil moisture, right? I show you my soil moisture example, but also air temperature, soil temperature. Um, we have sensors that can measure snow depth. We have to check them with rulers, right? So they're not fail-safe. Um, and so I have huge volumes of data that I have to deal with, right? Because when you have, you know, dozens of sites that are collecting measurements every 15 minutes, 24 hours a day, 365 days a year, you just have a huge volume of data coming in that you have to analyze. And some of the AI tools can really help with that. I end up actually writing a lot of code to analyze data. There's too much data to analyze in a spreadsheet, right? That's just not possible. And so AI can be really helpful in helping me come up with commands to code and use because that can be really hard and tricky. So that's really helpful. I would say that the parts of my job where it's more challenging is more in the classroom. So I am a teacher, right? So I teach college students. And so figuring out how to help students use AI to support them without sort of substituting them understanding the science, the content, learning how to write and having critical thinking skills. Those are probably the biggest things, but very helpful for analyzing data for sure, right? But AI isn't failed safe. Even though I use it a lot to help me write code, it often suggests the wrong thing. And so, you know, you have to like stay on your toes with that.
Yeah, makes sense. Speaking of data, one of the questions from a student, they're
Mhm.
wondering about the highest or craziest outlier that you've collected. Is there anything super interesting with those?
Well, let's see. Outliers are tricky because you have to spend a lot of time trying to understand if that data point is real or if it's because someone wrote down a measurement wrong or the sensor was malfunctioning. Uh, some of the outlier data that I've seen that has been fascinating is when we've had droughts. So I get really interested in understanding how changing winters were affecting growing season moisture because over the past 10 years, there's been a couple of winters where we've had very little snow. And those winters were followed by summers where there was very little rain. And so we've ended up in this sort of 1-2 punch situation where then we have really dry conditions. And so we have these moisture sensors that are measuring like 0.05% water in the soil, just like no water, like incredibly crazy dry conditions. And I look at those numbers and I think, are those real? Is that really how dry it is? And so those would be some of the extreme data that I've seen in terms of how interesting they are. Like, wow, it's really that dry. And we would check that by going out and actually collecting soil and, taking it back to the lab and analyzing it a different way. And so super dry conditions that we've measured that are really outliers for what we would expect to see in our area. Absolutely.
Interesting. Some students in Salem, New Hampshire want to know if we can expect winters to disappear in our lifetimes.
It's a great question and something that we've thought about a lot, my colleagues and I. And the answer is it depends, right? So we had a paper that came out a few years ago that explored what winters would look like across New England through 2100 using different scenarios of greenhouse gas emissions. And greenhouse gases are what are the key ingredients in driving warming in our climate system. Um, and so it really depends on what collectively we as a society do. right? So if we reduce our emissions to a level that stabilizes by 2040, then we can expect to see some cold and some snow in some parts of New England into the future. If we don't, and we continue on a worst case scenario trajectory, then many places will lose snow and lose cold. It's an interesting question the way that it's phrased. I've spent a lot of time thinking about this because it's not like December, January, and February go away on the calendar. These months still exist, but the conditions that we're used to expecting and that our ecosystems are used to expecting could change. And so what we can expect depends on what we do. Really, it's not inevitable that we lose the cold and the snow completely.
Yeah, definitely something that sounds really scary, but we talk about this a lot too here with students, that there's a lot of things that we're doing right now to combat climate change and to make sure that our winters stay cold.
Right.
And we just have to keep doing that and do more. And then we have another question from Ed Lindsay's class,
Hmm.
which is, are soil organisms equally active in the winter or more active in the winter than other seasons? Or are they active in different ways?
It's a great question. So soil organisms are in some ways really similar to any other organism, which means that um, as temperatures increase, usually metabolic activity increases. Warmer temperatures usually mean more activity, and that's true for most things, right? It's true for soil organisms, it's true for trees, it's true for us, right? And so as temperatures get warmer, you tend to see higher rates of biological activity. But, right, there's always a but. Um, there, it's possible that some soil organisms are better adapted to deal with cold conditions than others, right? Those would be cryophilic organisms, cryo meaning cold and philic meaning love, right? Like organisms that love cold. And some soil organisms, there's been research out of Alaska showing that some soil organisms can be active to minus 39 degrees Celsius. And I don't know what that converts to Fahrenheit, but like really, really cold, right? And the what soil organisms do in the winter can be different from what they do during the spring and summer. So some soil organisms in winter might be better adapted to take advantage of different uh, conditions that exist in soil during the winter. So if you think about it, like, okay, in the fall, most of the leaves drop from the trees, right? So you have all this leaf litter from oaks and maples and beech trees, and then it snows, right? And so then you have organisms in the soil beneath the snowpack, and some of the ones that are active in the winter are really good at taking advantage of the feast that has just sort of arrived, right, in the form of all this leaf litter, and might be better suited to decompose that leaf litter that arrives in the fall. In the summer, right, you have trees that are growing. Um, and as they're growing, right, as the leaves are growing on the tops of the trees, the roots in the soil are actually very leaky. They leak a lot of sugars and carbohydrates out into the soil around them. And so soil organisms during the summertime are really good at taking advantage of that really fresh, really sugary material that's coming out of roots. And so you can also think about it like the winter, the organisms that are active in the winter are better able to deal with more of the fibrous, maybe less tasty leaf litter. And the ones in the summer are like eating candy, right? They're feasting all those sugar that's leaking out of roots. And so partly depends on temperature and it also depends on what food is around.
Very cool. That's crazy that some of them are able to be active like at such cold temperatures.
Yeah.
And I did look it up. Minus 39 Celsius is about the same in Fahrenheit. It's at that
Yeah.
point
I
where
thought so, but I was
they're
like,
Um, Well, thank you so much. I think that's about time for our call. Um, I'm going to put a link into the chat for anyone who's interested in learning more about the Globe Phenology campaign in North America. And I will also put that into the email that goes out to all of our classrooms. But thank you so much, Dr. Contosta. Um, and thank you everyone for joining.
Thank you so much for having me, and thanks for all the great questions.